Continuing on here with our discussion of titrations, let's talk about what we'll do if we have a weak acid that is an unknown and a strong base that we are using to titrate it. So usually with these titrations, what we're going to be trying to find is the pH at different points in the titration. We won't always be doing this, but it is something that we need to know how to do. We need to know how to find the pH at the beginning, in the middle, and at the end of a titration, because we need to know what's going on in the solution. So we're going to have different rules for finding the pH based on the region of the titration that we are looking at. So for example, the initial pH of a weak acid titration is only going to have the weak acid present, because if it's the initial pH, that means we haven't added any of our titrant yet. We actually haven't started the titration truly. And so the initial pH we'll find using, and actually these example numbers are not correct. Sorry about that. But we'll find it just like any other weak acid equilibrium. So if you remember the weak acid equilibria from way earlier in this chapter, you're going to find the pH just in the same way as that. So if you were titrating acetic acid, you would just treat it like a weak acid with acetic acid. That's all you would do. It wouldn't be anything special. Once you start putting in the base, however, now we have to do it differently. We can't just treat it like a weak acid solution, because once we start adding in that base, a significant portion of our weak acid that we started with will get turned into its conjugate base. So it's not going to be just a simple weak acid solution anymore, where the vast majority of the molecules are still in the form of the acid. Now we will have a significant number of them turned into the conjugate base, which you might remember was the very definition that we used to describe a buffer. A buffer was a solution that had a significant concentration of both the weak acid and its conjugate base. So, for the region between where we start the titration and the equivalence point, we are going to treat the titration like a buffer. Because it is actually. It is a buffer. We have a solution with significant concentrations of weak acid and weak base. That is the very definition of a buffer. And so what we're going to do is we're going to do the same thing we did back in the buffer videos. We're going to do a little bit of stoichiometry to work out exactly how much of our weak acid and weak base are present, and then just plug those into the Henderson-Hasselbalch. So nothing new there. We do have a kind of unique situation here with what we call the half neutralization point. So the half neutralization point is where you have neutralized half of the acid that you started with. This is more limited than the other ones, simply because most of the time you're not going to know what the half neutralization point is, since you're working with an unknown. But if for some reason you do know where the half neutralization point is, which is to say you know when half of your molecule has been turned into the conjugate base and the other half still remains as a weak acid, then at that point the pH is equal to the pKa. And this actually just comes straight from the Henderson-Hasselbalch as well, because if you remember, the pH is equal to the pKa plus the log of the base over the acid. And so if you have equal amounts of these two, then this whole thing just becomes 0, and so you just have the pH is equal to the pKa. So less useful, but still sometimes is useful. So this is just reviewing again what we talked about with the buffers, where you know what you started with, you do the stoichiometry to figure out what the concentrations of the weak acid and conjugate base are, and then you plug those into the Henderson-Hasselbalch. So that's just reiterating that. Now, when you're at the equivalence point, In a strong acid and strong base titration, things are really simple because the only thing that you make in the neutralization reaction is water. But when you have weak things present, it's not the case. So at the equivalence point, if you started with a weak acid, every single last one of those weak acid molecules has been turned into its conjugate base. So however many moles of HA you started with, you're going to have that same number of moles of A- at the equivalence point, and that A- is a weak base. So, because we know exactly how much of the weak base is present, and we know the concentration of that because we've been keeping track of how many mils of base we've been adding, we are going to treat the solution at the equivalence point like a weak base equilibrium. Again, that example number is wrong, but if you remember back when we were talking about weak bases, I believe we did a weak base problem with ammonia, I think. It would be just like that. We would plug everything in just like a weak acid, but we would use KBs instead of KAs and all that good stuff. And so then past the equivalence point, so if we go past the equivalence point and keep adding more strong base, at that point the strong base has nothing to react with other than the water. And so it's just going to make more OH-, and that is going to be by far the main thing that affects the pH. Technically the weak base will still be present, but it's going to be so overwhelmed by the strong base that we don't have to worry about it anymore. So past the equivalence point, all we're going to do is a little bit of stoichiometry, or just unit conversions, or whatever it is we need to do to work out how many moles of OH- have been added, divide by the total volume of the solution at that point, and then just plug that into either the POH and convert that into the pH, or you could convert the hydroxide concentration into H+ and plug that into the pH. Remember, there's two different ways to do that, just whichever way you feel comfortable with. Alright, so those are all the possibilities. Those are all the things that could be asked of you to find, all the different scenarios of finding the pH in a titration. Now I want you to notice here, none of these are new. Every single last one of these we've done before. We've just not put them together. The initial pH, it's just a weak acid equilibrium. We've done that. Between the initial pH and the equivalence point, that's just a buffer. We've done that. At the equivalence point, that's just a weak base solution. We've done that. Past the equivalence point, all we have to worry about is the amount of strong base present. We've done that. Everything that we're doing here, we have done before. There's actually nothing new. It's just we've never had it all together like this. We've never had a scenario where we could have all four of these happening simultaneously. So it is a bit different because of that. The combining of things is not something to be flippant about. Like, it can be difficult to combine concepts like this. But I just want to reiterate again, we've done all this before. These are all things we've done before. So don't stress out about them too much. Oh, right. I think I'm actually going to give this problem its own video because it's pretty long. So you can see I've even given it 3 slides here to work on. So I'm going to go ahead and stop this video now, but in the next video we're going to be doing this practice problem, which puts all of that stuff that we just talked about into effect. So we're going to be finding the pH at multiple points, as well as just working out different volumes and things concerned in the titration. So I will see you in that next video, and the whole video will just be working out this problem here.